Welcome to the next lecture in power system modeling. Here we are going to discuss the sequence impedance and sequence networks. So the sequence impedance are the impedances offered by the power system components to positive, negative and zero sequence current. We have seen in the previous lecture that whenever a system is unbalanced, it is easy to analyze such type of systems by converting the unbalancing to symmetrical components which involve the positive, negative and zero sequence current. Now the impedance that is offered by these currents due to the circuit components may be generator, motor or any other devices which is used in the power system network. So that impedances are known as sequence impedance. Now, so positive sequence current will give positive sequence impedance, negative sequence current will give negative sequence impedance and zero sequence current will give zero sequence impedance. So we see that the sequence impedance given by different currents, positive, negative and zero, are different and they are respectively known as positive sequence impedance, negative sequence impedance and zero sequence impedance. The voltage drop that is caused by the current of a particular type of sequence, whether it is a positive, negative or zero, will depends on the impedance of the element to the circuit current. So whenever we have some components, so the components will have some impedance. So whatever may be the sequence we are dealing with, whether we are dealing with the positive sequence, negative sequence or zero sequence, we have to compute the voltage drop for that particular sequence. Now, the impedance or reactance diagram formed using the impedances of any one sequence only is called sequence network. So, corresponding to positive sequence impedance, we can have one network. Corresponding to negative sequence impedance, we can have one other network, and corresponding to zero sequence impedance, we can have other network. So, such type of networks are known as sequence network. So we see here positive sequence impedance give positive sequence network, negative sequence impedance will give negative sequence network and zero sequence impedance will give zero sequence network. So this is the introduction for sequence impedance and sequence network. Now we will discuss the power system components one by one and try to identify the sequence circuit. So the first power system component we are going to take is the load. So for example, take a star connected load. So if you have a star connected load and the system is balanced, it means the impedances in each of the phases is equal and it is being grounded with a neutral impedance. Then in that case, the neutral current flowing, if we apply a KCL equation at this node, that is the neutral, will have the sum of the current IA plus IB plus IC, which are the phase currents. So if we split the current IA, IB and IC in terms of the positive, negative and zero sequence current, then we'll have 3 times IA naught and IA1, IB1 plus IC1. So these are corresponding to the positive sequence current and these are corresponding to the negative sequence current and this is the zero sequence current. We know that the sum of the positive sequence current will be 0 and the sum of the negative sequence current will be 0. So the neutral current is equal to 3 times IA naught. This means the neutral current only the zero sequence current will be involved. So in the neutral only the zero sequence current will be involved. Now there will not be any positive or negative sequence current flowing out of the neutral point. So we see that whenever we are computing the neutral current, only the zero sequence current is involved. So there will not be any positive or negative sequence current flowing out of the neutral point. Now the voltage drop between the neutral and the ground. So this is your neutral point and this is your ground point. So the voltage drop is involved with respect to the neutral impedance Zn. So the voltage drop is given by 3 times Zn into Ia naught because the neutral current is basically 3 times Ia naught. So this term will be multiplied with Zn. that is the neutral impedance. So if we draw the circuit, we have a balanced circuit ZY in each of the phases and Zn being the neutral impedance. So here we see only the zero sequence current is flowing in the network, and the total drop in the neutral impedance is 3 times the zero sequence current multiplied with the neutral impedance. So the voltage of phase A, if we apply the KVL equation, then the voltage of phase A is equal to VAN, that is the single phase voltage of A line to neutral voltage, plus the drop in the neutral impedance, which is equal to 3 times Zn into Ia0 plus VAN. Then if we write the other expression for the other two phases, then here we have got VA, so other phases VB and VC we have to write, and we have to form in this form. So it will be VAN plus VN for the phase A, and VB is equal to VBN plus VN, VC will be equal to VCN plus VN, and now this can further be break up into this format. So 3 times Zn Ia0 is the drop across the VN network, and here the voltage of the phase A, B and C is correspondingly the current of the phase A, B and C multiplied with the impedance ZY, because the system is balanced. Now if we pre-multiply both sides of the above equation by the matrix C, we have seen this matrix C in the previous video lectures, that the matrix C will be used when in order to analyze the symmetrical components. So the VA012, that is the zero sequence, positive sequence and negative sequence of the phase A, will be equal to ZY, that is the impedance of any one of the phases, multiplied with the current, zero sequence, positive sequence and negative sequence of the phase A, plus 3 times Zn into Ia0, that is the zero sequence current, multiplied with the C matrix. So this can be break up in further, and we can write in the matrix format. So the zero sequence voltage, positive sequence voltage and negative sequence voltage for the phase A is equal to ZY, that is the per phase impedance of any star connected network, multiplied with the respective sequence current, plus 3 times Zn into the zero sequence current, and the positive sequence current and the negative sequence current will be 0. So we find that the zero, positive and negative sequence voltages only depend on the respective sequence component current. So whenever we are trying to find the positive sequence voltage V1, so it will be depending on only the positive sequence current Ia1. When we are trying to find the negative sequence voltage Va2, so it will be depending on the current Ia2. Similarly, if we are finding the zero sequence voltage of the phase A, so it will be depending on the current zero sequence of the phase A. So while the positive and negative sequence impedances are both equal to ZY, so whenever we are drawing for a transformer, the positive and negative sequence impedances are equal to the per phase balance voltage. The zero sequence impedance is given by ZY plus 3 times Zn. So Zn being the impedance in the neutral, so we have see that Z1 is equal to Z2, that is the positive and negative sequence is equal to ZY, whereas your Z0, that is the zero sequence impedance, is equal to ZY, that is the per phase impedance plus 3 times the neutral impedance Zn. However, if the neutral is grounded directly, then Zn is equal to 0. In this case, this will vanish, and you will have the zero sequence impedance Z0 is equal to again the per phase balance impedance of a star connected network. Now if the neutral is kept floating, then Zn will be infinite, then there will not be any zero sequence current flowing in the circuit at all. So in case to follow the zero sequence current, you can't keep the neutral open. So if the Z is equal to infinite, then obviously your zero sequence current will be equal to 0. There will not be any zero sequence current. So here we can see the circuit for the zero sequence. This is for zero sequence, this is for positive sequence, and this is for negative sequence network. So we see that the positive sequence and the negative sequence impedances will be equal to zy, and here you have the positive sequence voltage, here you have negative sequence voltage, and here you have positive sequence current flowing and negative sequence current flowing. So z1 is basically the positive sequence impedance and z2 being the negative sequence impedance. So both z1 equal to z2 is equal to zy. However, if we see the zero sequence impedance, we have the sum of zy plus 3 times zn is equal to z0. So your z0 is equal to zy plus 3 times z0, and here you have the zero sequence voltage and the current flowing is zero sequence current. Now, in the case where you do not have any connection with the neutral, so neutral is not there, so here in the neutral is not there, so that there will not be path for the zero sequence current because it is an open circuit. So here he will have an open circuit. So obviously your neutral has to be grounded in order to flow this current through the network. Now we'll go for the delta connected load. So we have seen the star connected load. Now let us try to find the sequence circuit for the delta connected load. Now the delta connected load balance system will have an impedance Z delta in each of the phases. So here there is no neutral point. So you know that in a delta connected network you will not have any neutral. So no neutral will be there in the delta connected network. So the voltage VAB, VBC and VCA, that is the line voltages, are equal to the product of the current that is flowing in the line multiplied with the impedances. If we add all these three voltages, then we get Z delta into the sum of the current flowing in the line. Now if this VAB plus VBC plus VCA, the sum of the line voltages, we can split up in the form of VAB can be written as VA minus VB. Similarly, VBC can be written as VB minus VC, and VCA can be written as VC minus VA. Sum of the voltages will be equal to 0. Then in that case, we can find out that the line voltage of the zero sequence and the line current will be equal to 0 because there is no neutral involved in the delta connected load. So in the delta connected load you do not have any neutral point, so obviously the zero sequence current has to be 0. If the zero sequence current is 0, obviously the voltages involved will be 0. So no zero sequence circulating current for a delta connected load. So whenever your load is delta connected, your zero sequence current will be no. There will be no zero sequence current. Positive and negative sequence impedance for this load will be equal to Z delta. So it means Z1 is equal to Z2 is equal to Z delta, and the zero sequence current is equal to 0. Z not equal to 0. So here if you draw the network, you will see that here you will have a open circuit. Because there is no neutral current involved, so there is no path for the neutral current and there is no path for the zero sequence current. However, there will be a circulating current flowing here, so that circulating current can flow in this part. So that is being shown. Now the next component that we are going to take is the synchronous generator. Okay, so in the synchronous generator per phase equivalent circuit, if we see that each phase will have a individual voltage source or the EMF in series with a RL system or the RL internal impedances, and within the inductance you will have a mutual inductance. So each inductor will be related with a mutual inductance, and the neutral point, because it is a star connected network, neutral point will be grounded in terms of the neutral impedance Zn. Then the neutral current, that is the sum of IA plus IB plus IC, will not be equal to 0. The reason being is that it is it is not balanced circuit, so your neutral current will not be equal to 0, because each phases will have a different drop, so neutral current will not be equal to 0. Now, if we write the voltage of an individual phase with respect to neutral VAN, then we can write it is as minus R plus j omega Ls into Ia, that is the current flowing in the phase A multiplied with the impedance of the network in the phase A, plus the mutual inductance of the two current IB and IC. So this inductor Ls will have a mutual inductance with respect to the C phase and with respect to the B phase. So that will have a sum of the current IB plus IC into the mutual inductance, and there will be an induced EMF EAN, the self-induced EMF EAN. So this can be properly arranged in terms of the current IA plus IB IC and EAN. Now, for the other two phases, if you write the equation and arrange it in matrix format, so voltage VAN, VBN and VCN are the single phase equivalent voltages with respect to the neutral. So it will have with respect to the current. So here you have the current IA, IB and IC, and this is the impedance of the network, which is this is the mutual inductance. It's 1 in terms of the current, and then you have the respective EMF of the circuit. So this is the respective EMF of the circuit. Now again we multiplied with respect to the transformation matrix C in both sides. So if you multiply transformation matrix on the both side, this VAN, VBN, VCN will be converted to the zero sequence, positive sequence and negative sequence network with respect to only one phase, that is A phase. Right? This current IA, IB and IC will be replaced with the zero sequence, positive sequence and negative sequence current for only one phase A. Similarly, this current IA, IB and IC will be replaced with the current zero sequence, positive sequence and negative sequence for any phase A. Similarly, this induced EMF for all the three phases will be converted into the zero sequence, positive sequence and negative sequence induced EMF for the phase A. So here we have a multiplying with a matrix C and C inverse. So synchronous generator are usually operated for the balance voltages. So EN and N0, N1 and N2 will be equal to 0. So whenever the system is balanced, you will not have the zero sequence or the negative sequence. Only one sequence you will have, that is the positive sequence. Whenever a system is balanced, you do not have a zero sequence or you do not have a negative sequence. You have only one sequence, that is the positive sequence. So EAN1 is equal to EAN. Therefore, we can further write this equation and make this voltage as 0 and this voltage as 0. So the zero sequence voltage will be 0 and the negative sequence voltage will be 0. Only you will have the positive sequence voltage. So there will be only positive sequence voltage. So if we separate them, the terms out in terms of zero sequence, positive sequence and negative sequence for phase A, then you will have a impedance Z multiplied with the current that you have for the zero sequence, positive sequence and negative sequence, plus you will have only EAN in the positive sequence component. Here you will have plus 0 and here you will have plus 0. So this can be written in the form of, you will have minus Z G naught A naught, that is the zero sequence voltage drop. This will be having the positive sequence and this you will have negative sequence network. So when you see the negative zero sequence voltage, you will have VA naught is equal to minus of ZG naught into IA naught, where this ZG naught is basically the total impedance, that is equal to R plus J omega Ls minus 2 times the mutual inductance, So this G naught is equal to this. Similarly, when you are trying to write VAN2, that is the negative sequence, it is equal to minus of Z2 into Ia2. So here negative sequence current is involved, and Z2, that is the total impedance offered in the negative sequence current. So this is equal to this. So here in a star connected load, if the generator is connected with a star connected load, then VA1 equal to VN1 we have seen, and VA2 is equal to VN2, since the neutral current does not affect this voltage. The neutral current will only affect the zero sequence. It will not affect the positive sequence or the negative sequence. Also, the zero sequence current voltage VA0 is equal to VA0 plus Vn, and you know that this Vn is equal to 3 times Zn into Ia0. Then in that case you can write Va0 is equal to minus Zg0 plus 3 times Zn plus Ia0, which is equal to minus Z0 into A0. So this total impedance of the circuit is corresponding to the zero sequence. So zero sequence impedance, the total one, is equal to Zg0 plus 3 times Zn. Now here we have the original circuit. So this circuit is basically the original circuit. So in the original circuit we have three phases, A, B and C, and each will have an induced EMF, and there will be an impedances connected, and it is grounded with a neutral impedance, and the current is flowing IA, IB and IC in each of the phases, and you have a neutral point. Now if we draw the positive sequence network and its single phase equivalent circuit, then you will have in each phase you will have a EMF and the impedance, which you, when you convert it in positive sequence, because the system is balanced, you will have one voltage source, that is the internal impedance, and Z1. So this one is Z1. Z1 is basically the positive sequence impedance. Here you will have positive sequence voltage, and here you will have positive sequence current. Now for the negative sequence network, you will not have any EMF. That you can see it in the equation itself. So when you are writing an equation for VAN2, you do not have any induced EMF, whereas whenever you are writing an equation for VAN1, you are having an induced EMF. So here you do not have an induced EMF in the circuit, which is replaced only one impedance Z2, and you have a negative sequence voltage and negative sequence current. This is a single phase equivalent for a negative sequence network. Now for a zero sequence network, we have seen that in the zero sequence network equation, voltage VA0 is equal to minus Zg0 into Ia0, where Zg0 can be written as Zg0 plus 3 times Zn. So that thing we are converting it. So here you have Zg0 plus 3 times Zn. This together sum is made to be Z0, that is the total zero sequence impedance. Then you will have a zero sequence voltage and a current flowing as zero sequence current. Now this neutral has to be grounded, otherwise you will not have this Z0, Zn. Now the next component that we are going to take is the transmission line. So we have discussed the load as well as the generator. Now let us go for transmission line. So in the transmission line, let us consider the self impedance of each phase as ZA. Okay, so you have three phase transmission line, and each phase the self impedance is equal to ZA, and the mutual impedance, let it to be ZAB. So between ZAA, that is the phase 1, and phase 2, your mutual impedance is ZAB. Between 2 and 3 also the mutual impedance is ZAB. Between 1 and 3 also the mutual impedance is ZAB. This is the assumption that we have taken. So your all the self impedances are equal. Now the this is the neutral involved, where Znn is the neutral impedance. So you have the three phase voltage as VAN, VBN and VCN, and the current flowing is IA, IB and IC, and there is a neutral current IN. And here you are getting a voltage, after drop you are getting a voltage VA dash N dash, VB dash N dash and VC dash N dash. So since the transmission line is assumed to be symmetric, so we know that transmission lines are generally symmetric in nature. we further assume that the mutual inductance between the conductor are the same, and so the mutual inductance between the conductor and neutral are this quantity. So ZAB equal to ZBC equal to ZCA, which is equal to Zm, that is the mutual impedance, and ZAN, ZBN and ZCN are also equal. Then in that case, if we apply the Kirchhoff's voltage law for the phase A, VAN, so you are getting VAA dash plus VA dash N dash plus Vn dash N. This we can easily see it in the equation. So this VAN, where you will have, that is the drop along this part, and then you are obtaining here, and then you are having a drop across Zn. So you can form a complete path from here to write the Kirchhoff's voltage equation that we have written for the phase A. So this value we have written for the phase A. Now we can redraw the circuit based on the KVL equation that we have. So based on the KVL equation, we are redrawing the circuit. So here the input is VAN and the output is VA dash N dash, and these are particularly the drop that are associated with the circuit corresponding to the volt current IB, IC and neutral current. So you have ZAB, ZAB and ZAN, and here you have ZAN, AN and AN. So this is basically the neutral impedances, and here you have the mutual impedances, and this one is the self impedance and this one is the neutral impedance. So here again we can write an equation of VAA dash equal to the drop in ZAA, that is the self impedance, into the current of IA. ZAB is the mutual impedance into sum of the current IB plus IC. ZAN is the neutral impedance of the phase A and the current IN. So VN and dash is basically ZNN into IA plus ZAN into sum of the current IA plus IB plus IC. Then we can usually see it that VAN is basically this quantity, VN is basically this quantity plus this quantity and minus this quantity. So we can have seen that in the equation, so we can substitute it and write it in the better format in terms of IA, IB plus IC and IN equal to ZAA minus ZAN, ZAB minus ZAN plus ZNN minus ZNN. So this is the subtraction of the voltage of VAN, which is here in the input side. So this is the input and VA dash N dash is the output side. So this is the output voltage. So we are basically writing the KVL equation in this complete loop. So neutral current will have a path minus of IA plus IB plus IC. Then on substitution for phase A of the circuit, we are rewriting the equation VAN minus VN dash, and then we are finally getting this value. So after simplification of this equation, we will be getting this equation. So we are more interested in the final solution. So VA dash is equal to Z dash into IA plus Zm into IB plus IC. Zm is the mutual impedance, Z dash is the self impedance. So when we are dealing with the phase A, you are having a current IA, and for the mutual inductance you are having a current IB plus IC. So now we can split up and write it for the all the phases. So this is for phase A, this is for phase B, and this is for phase C. Here we can see that ZS all are having in the diagonal, that is the self impedance, and off diagonal elements are the mutual impedance, and this is a symmetric with respect to the diagonal elements. So this is equal to product of IA plus IB plus IC. Now this can be broke up into the zero sequence, positive sequence and negative sequence corresponding to only one phase A by multiplying with a transformation matrix C on both the side. So if you multiply C on both the side and further you are just doing some simplification, you will get the zero sequence, positive sequence and negative sequence for the phase A is equal to this, which are only the diagonal elements we are getting. The first one is ZS plus 2Zm, the other one is ZS minus Zm, the other one is ZS minus Zm. So here we can see that the positive and the negative circuit is having an impedance ZS minus Zm, and the zero sequence we are having an impedance ZS plus 2Zm. So the sequence circuit then can be obtained. So each way, the zero sequence, positive sequence and negative sequence impedance, you have zero sequence current, positive sequence current and negative sequence current. So here you have zero sequence voltage, positive sequence voltage and negative sequence voltage corresponding to phase A with respect to neutral. So your neutral is basically grounded. So here you have a voltage V A dash N dash. So we have seen that the Z1 and Z2 are equal, which is equal to Zs minus Zm. Now Zs is basically the self impedance, we can write as Zaa, and Zm is basically the mutual impedance, which we can write minus of Zab. Similarly, the zero sequence impedance, we have seen Zs plus of 2 Zm, and this can be further broke up in terms of self and mutual impedance as Zaa plus 2 times Zab plus 3 times Znn plus minus 6 times Zam. So this is the total zero sequence impedance of the transmission line, and the positive and negative sequence impedances are equal, and we can draw the sequence circuit in this form. Now, before we do the sequence circuit for a transformer, because we have deal with some of the devices, so we have deal with a load, second we have deal with synchronous machines, okay. Now in and third we have deal with transmission line. These three devices we have covered. Now the fourth device that we are going to take is transformer. So in order to understand the transformer sequence circuit, we will quickly revise some of the transformer connection that. So let us quickly revise the transformer connection. So in the three-phase transformer, the first connection that we are going to discuss is star-star. So when you have the primary connected in the form of a star and secondary connected in the form of a star, you have a line voltage VLL and the phase voltage or the neutral voltage is VLN. So capital letters we are using for the primary circuit, and the small letters we are using for the secondary circuit. So the transformation ratio, you will have N1 is to N2 when you have the single phase equivalent. So this is the three phase transformer. Now the single phase equivalent for the three phase transformer, if you do, then it is N1 is to N2. Then the line voltage, the ratio of the line voltage to neutral for the primary circuit, primary circuit to the secondary circuit is N1 by N2. Then if we do it, then in this case we get the impedance ZH is equal to N1 by N2 square into ZL, which is we can write in terms of the voltage VLL square by VLL into ZL. Now if the second connection we are using as star delta transformer. So we know that in the delta your per phase equivalent circuit will be N1 is to N2 by root 3. So this is the difference in the first circuit. In the first case you are having N1 is to N2, but here in the first circuit we were having N1 is to N2, but in the second circuit we will have N1 is to N2 by root 3. Whenever the delta will be involved, then there is a phase difference, and due to which this root 3 is appearing, which will be seen in the ratio of the voltages and the turns ratio also. So the third one, you have delta star connection. So in the delta star connection, you will have root 3 divided by root 3 appearing in the primary circuit. So N1 by root 3 is to N2, which will again will impact the ratio of the voltages and the impedance. So if you have a delta transformer, so you will have under root N1 by under root L, N1 by under root root 3 is to N2 under root and root 3. So in the first case when you have star transformer, and the last case you have delta transformer, since root 3 and root 3 will cancel out each other, so in this case also it will be N1 is to N2. So there will not be any major changes. Now we'll start the sequence circuit for transformers. So first transformer connection is star connected network that we are going to see. So in this case the primary is connected in star and secondary is connected in star, and both are grounded with respect to the neutral in terms of the neutral impedance, and here you have the current cap IN flowing. However, the direction of the current is reverse in the value of IN for the secondary circuit. Then in that case the voltage of phase A, so let us take the phase A voltage. So VA is equal to VAN plus VM. This is the Kirchhoff's voltage law that you can apply in the neutral point. VN is the drop in the neutral impedance. Then this VN can be written as 3Zn into IA0 that we have seen in the load side. And then the VA can be broke up into VA0, VA1 and VA2, which is the zero sequence voltage, positive sequence voltage and negative sequence voltage. And the phase voltage VAN can be again broke up into three components, and here we can write the drop. So since the direction of the secondary neutral current is opposite to that of the primary neutral current, we can further write down the equation for the secondary side as well. So small letters are corresponding to the small secondary side. So here one term alpha will appear, that is the turns ratio. So alpha is basically N1 by N2 is equal to Vn by Vn because this transformer is star-star transformer. So Vn is equal to Vn by alpha. So taking the advantage of the turns ratio, we can write down in this equation, previous equation, and try to find out what is the value of VA0 plus VA1 plus into VA2 multiplied by alpha. We'll get an equation in this format. So here we have star-star transformer and alpha being the turns ratio of the transformer. So we are writing and converting the equation in the format of the positive sequence, negative sequence and zero sequence network to find out what impedances do it offer for the positive, negative and zero sequence network. So we can see that the positive sequence and negative sequence impedance voltage for the primary circuit is alpha times the secondary voltage, alpha times the secondary voltage for the positive and negative sequence. However, the zero sequence network equation relationship between the primary circuit and the secondary circuit is a little bit different. You will have a ratio, you will turn in terms of Zn plus N1 by N2 square into Zn. So positive and negative sequence impedance are same as that of transformer leakage impedance Z. So whenever we are trying to find Z1 is equal to Z2 is equal to Z, that is the leakage impedance, but the total zero sequence impedance we can see from this relation is this one. So it is equal to Z plus 3Zn plus 3 times N1 by N2 square into Zn. So this is the total zero sequence impedance which is offered by a transformer under the connection star-star network. So here we can draw the network. So for the zero sequence, the total impedances offered is Z, that is the leakage impedance, 3 times Zn plus 3 alpha square Zn. So these together will form the zero sequence impedance, and the current flowing is IA0 and the voltage is VA0 here. So now in suppose you will have the neutral solidly grounded, then in case Zn is equal to Zn equal to 0, means the primary circuit is solidly grounded and the secondary circuit is also solidly grounded, then in that case Zn is equal to 0 and here also Zn is equal to 0. Then in that case the zero sequence impedance will be equal to Z, because you will not have a term Zn here, so this term will vanish and there will be a term known as only Z. Okay, and then we can draw the circuit with respect to grounded, neutral and ungrounded. So under the case of ungrounded system, there will be an open circuit because the ground is not involved, and in the case it will have Z dot as the grounded neutral. So Z naught is basically Z plus 3 times Zn plus 3 alpha square times Zn. Now if you have a delta connected transformer, we see that there is no neutral current involved, so neutral current is 0, so it will have the zero sequence current will be also 0 because there is no neutral for delta connected transformer. So the voltage of AB phase line voltage is equal to VA minus VB. VA can be split up in the equation that in terms of the positive, negative and zero sequence voltage. VB can be split up in terms of positive, negative and zero sequence voltage. So it will be equal to VAB1 plus VAB2. So we can, because this term will cancel out each other and it will be VAB1 plus VAB2, and then VAB can be written in this format in terms of the alpha, that is alpha is the turns ratio which is equal to N1 by N2 into VAB. Then the VAB, which is the voltage of the line VAB, can be written in terms of alpha is equal to VAB1 plus VAB2. So the sequence component of the line to line voltage can be written in terms of sequence component of the line to neutral voltage. Then VAB1 and VAB2 we have to find out, and it is 30-degree phase shifting is there, and root 3 we know that the line voltage is equal to root 3 times the phase voltage. So that concept we are basically using here, and then we add up both two. So you add this one and 2 to find, so you'll get this equation. Then your VAN1 is equal to alpha times VN1, and VN2 is equal to alpha times VN2 that we are getting. So the positive and negative sequence equivalent circuit are represented by series impedance that is equal to leakage impedance of the transformer. So here Z1 is equal to Z2 is equal to Z, that is the leakage impedance of the transformer. So the delta connected winding does not provide any path, so zero sequence current will be 0. So as discussed, you will not have a zero sequence current. So here we can see the circulating current will be here, and you will have a zero sequence impedance, and which will be closed, and you will not have a path for the zero sequence current. Now the next connection you have star delta connected transformer. So we see that the star side you have a neutral impedance, however in the delta side you do not have any neutral impedance, so Zn equal to 0. In this side you don't have. So even though I naught in the primary side will be there, because here your neutral current, zero sequence current will flow, but here there will not be any zero sequence current in the delta side. So the zero sequence current will be 0 because it will not have any path to flow in the line. So there will be only circulating current in the magnetically of the primary winding. So in that case, we have already seen that VAN is equal to alpha times VAB, and if we again write the equation of the phase A and split up the equations in terms of zero sequence, positive sequence and negative sequence, so we are basically getting a term 3Zn into IN naught here. So split up into 3 zero sequence, positive sequence and negative sequence, so you are basically getting the equation in terms of this equal to, so these three terms you are basically getting. So the total zero sequence impedance is equal to Z plus 3 times Zn. Now primary and secondary sides are not connected, hence an open circuit will be there between them because you do not have any zero sequence path flowing due to the absence of the neutral in the secondary side. Since the zero sequence current flows through the primary, a return path is provided through the ground. So if the neutral Zn is equal to infinite, means the primary circuit which is star connected, if the neutral is not grounded, the zero sequence current cannot flow in the primary side as well. In the previous case when there was Zn, so at least the primary current can flow, but now the primary current will not able to flow in the network. So sequence diagram can be shown as Z0 is equal to Z. So in this case, if you see it, then in that case you will have the positive sequence and negative sequence will be equal, which is equal to Z. So these are the positive and negative sequence. Now here in the C case and D case, you have the zero sequence with grounded and ungrounded. So if the ungrounded is there, then there will be open circuit. If the grounded is there only in the primary circuit, it will be 3Zn, and secondary circuit will be open because secondary circuit is connected in delta and primary circuit is connected as star grounded system. So total symbol wise, if you do it, so if the circuit is star grounded, then your zero sequence impedance will be Z plus 3Zn plus 3 times Zn. If you have star grounded and the secondary is star, so you do not have any path flowing here because it is open. If you have a delta connected network, only the current will flow in the circulating part. This path is open, this path is open. If you have a star grounded and delta, then in this case, because here is a delta is there, so here there will be open circuit and here only zero sequence current will flow. If you have a star delta network, no ground is involved, so open circuit on both the sides. So in the primary circuit and secondary circuit, you will not have any path for the zero sequence current. Now let us see, if we have a one line diagram of having a transformer 1, transformer 2 and transformer 3, and all connections are given for transformer 1 is delta star, transformer 2 is delta star grounded, then transformer 3 is star grounded into delta for the primary and the secondary circuit. Then you can easily convert this one line diagram into the reactance diagram, that is the zero sequence network, after proper evaluation of the connection, which type of connection it falls. So you can have form the sequence network, how it is open and where it is closed to form the zero sequence network. So in case of a transformer, it has to be easily seen whether your ground is involved to flow the zero sequence current or not. So if you have a delta star grounded system, then only the zero sequence current will flow in the secondary side. There will not be current in the primary side. So sequence network is basically the positive, negative and zero sequence network, which is formed separately by combining the sequence circuit of individual element. So the individual element we have seen all: load, transformer, transmission line, synchronous machine, and the positive, negative and zero sequence network are formed individually. However, we have to do certain type of assumptions. First assumption is, apart from synchronous machine, network is made up of static element. We see that only synchronous machine is rotating and other all devices will be static, and the voltage drop will be corresponding to a particular sequence current. Other current will not involve. Positive and negative sequence impedance are equal for all static circuit elements. So whenever any static circuit elements are involved, everywhere the positive and negative circuit element will be equal and zero sequence component need not be the same. Okay, and transient positive and negative sequence impedance of a synchronous machines are equal. So this transient case, sub-transient case in fault we'll study, we'll see that in sub-transient positive and negative sequence impedance of synchronous machines are equal, and voltage source are connected to the positive sequence circuit of a rotating machine. So the voltage source is only connected with positive circuit, a positive sequence, and not with negative sequence or zero sequence in case of a rotating machine. No I1 and I2 will flow between the neutral and the ground. So these are certain assumptions or finding that we have done in case of a sequence network. Only the zero sequence current will flow only when you have a ground point. Otherwise the zero sequence current will not flow, and whenever you have a voltage source, connect it with the positive sequence network only, and for each sequence you have to separately obtain the positive, negative and zero sequence network. So if you have a power system single line diagram which is involving all the components, suppose you have a generator, transformer, transmission line, again one transformer, grid, and then you have a load. So all these components has to be dealt with individually. So first you have to obtain the network elements, and then the positive, negative and zero sequence will be obtained individually for each of the component, corresponding to each of the component, how the components positive, negative and zero sequence component will be there, and then you have to draw the positive sequence, negative sequence and zero sequence for the entire single line diagram separately. So you have to obtain the positive sequence, negative sequence and zero sequence for all the elements, whether it is a transmission line, generator, load, you have a source, everything. So in this way we have complete the power system modeling concept, starting from the per unit system and single line diagram to the reactance diagram, and how do we obtain the sequence circuit. Thank you.